is that they use what are called kernels, essentially sliding windows of feature detectors that are passed over an image to detect salient features given the task at hand. There's a whole battery of those kernels, a few dozen even in simple networks, that are all passed over the network, kind of like you can picture it like running a loop over an image, and each one of those kernels is looking for a different kind of feature. And of course, what's unique in the AI approach is that those kernels are not hand tuned, they're not hand designed. They learn to detect what is unique and what varies in a collection of images. So, um, building on that as a deep neural network, the the another layer of convolutions is then applied over top of the result of those convolutions, and after that's done, a number of times over a significant number of layers of those convolutions, you end up with what is essentially a digest or an understanding of what the image looks like. So fundamentally, the network doesn't actually store studies as collections of pixels like you would with a digital photo. It actually learns to develop an understanding of what a body looks like and how a body varies. And so, on the one hand, you end up with a very condensed, very very succinct representation, but on the other hand, you end up with the ability to then generate high fidelity imagery out of that understanding with uh, almost arbitrary levels of precision. And I mean, to give a sort of human example, it's very easy for a human being to take a series of photos like if you were to see my face, I think my video is up right now. If you were to see my face straight on, and then another photo of my face from the side, and another photo of my face from this side, in your mind, it would be fairly easy for you to envision what uh, what an arbitrary number of rotations of my face would look like, what my face would look like from all kinds of angles. You could probably even picture what the back of my head looks like, although you've never seen, the back of my head. And so this model is similar to that. Even in the case of a low dose scan, where much of the information may be either occluded or ambiguous, the understanding that the model has of how a human body is constructed allows it to infer intelligently what it's seeing. Um, Maybe a specific example of that in the chest case might be if you imagine having a spherical nodule in the lungs. It's possible that the DICOM imagery that you're seeing has information for the top and the bottom of that nodule, which may be fairly small points. And a naive approach might be used outside of the AI kind of approach, may be to simply average information between those slices to try to figure out what's going on in between. And as a result, you might end up with something like a cylindrical observation there that really makes no sense in the context of the lung. A deep learning approach, like our model, would be capable of understanding what it's seeing to the point of being able to infer the presence of nodules of given physical characteristics. Um, yeah, I mean, I could keep going to the nth degree, Dave. I don't know if you have any areas you'd like me to focus on in particular, but
Yeah,
that's
yeah. Well,
the.
there's a question from the in the chat there
Oh,
about,
I missed that. Yeah,
and the question was, would you say CNN is the best approach today for image recognition problems?
yeah. I mean, when it comes to developing any model, I think it behooves the architect to evaluate, as wide a range of approaches as possible. I do think that CNNs are definitely the go-to family of models for image processing. Um, there's obviously, very interesting overlap there with other technologies in the space. Attention models and recurrent models can be very helpful when dealing with time series data that might be image related as well. But I think convolutional neural networks are absolutely the backbone of image recognition and computer vision.
Great, thanks, Ed. Yeah, I think there are a few images on here as well that I think we can share in the presentation. So we've got a couple of just fly through images. I'm not sure how well that animation is going to work on this call, but effectively, you know, there's kind of before and after images.
It
Uh,
works well.
Works pretty good. All right,
Yeah.
great. Excellent. Now, I don't actually know what I'm looking at there, but Dr. Lindsay would. But it's definitely giving you that, kind of before and after, so you can see that a lot of the noise within the scan on this particular slice has been significantly reduced, sharpening of edge features. One of the things that, certainly AI has the capabilities to do that humans do not. Humans, typically can only detect somewhere, I think it's up to about a max of 30 different shades of gray when we're analyzing these images. And clearly when we're using AI to analyze these images, we can get a lot more granular. And that can even come down to assisted things like finding the best windowing settings to look at an image to get you the highest contrast for a particular region. And that can be, typically trial and error and requires the experience. But in the case of an AI, we can really train the models to hone in on exactly what is the right windowing setting for that particular image. And it can also get back to not looking at these images the way we typically do, which is one of the advantages of machine learning and vision. Right now, we're looking at, different slice directions within the model, but really within AI, we could start actually looking at the entire 3D image all in one big scan or one big review. And the time to actually analyze these images is going to be, it's down to seconds as opposed to minutes or longer. There's a question here, Ed, about are we building the model from scratch or did we use a transfer learning approach?
Yeah, so this model was in fact trained from scratch. So we used a collection of images totaling about 15,000 for the initial training set sorry, not 15,000 slices, but 15,000 studies, and that was definitely enough for us to see very, very positive results. I mean, as you're seeing in front of you here.
That's great, thanks, Ed. So really, like this space is really exploding right now, and there are a ton of medical imaging startups in this space. I think, one of the things that we're going to be looking to do is actually pushing this model up into a cloud environment so that people can just give it a try. So we're likely going to integrate that with PACS archiving and have that as a way to push images securely into the model to see what the results look like. Some of these companies are also doing work that enables us to do a whole lot more. So, MD.ai is essentially a platform where models can be built in. Pre-built models can just be used. So it speeds up the time to get these image enhancement products to market. And there's a lot of money being invested in this space right now. So I think we're going to see some pretty radical advancements over the next couple of years. And there's a bunch of different tools and resources available out there right now. So, data sets are growing on a regular basis. That's something we're always looking for, or new data sets that we can work with. Right now, we've only done CT modeling or CT chest modeling so far, but we'd like to expand that to other regions. We'd like to also work on more direct diagnostic imaging and measurements. So, any image data or partnerships that we can build in that space are most welcome. Some of the platforms available out there are getting quite advanced as well, and a lot of this is being open sourced. A few of the research clusters, like the Stanford has their own version of AMI, the Artificial Intelligence in Medical Imaging group, and they are publishing pretty much everything freely and open source to the cloud. So that code is easily acquired and used and put into operation. And then just some of the standards around that have been built in cloud enablement. So PACS is a good example, just as the picture archiving capabilities for that, and gives us the ability to share both the images securely and the results. So Uh, Lots going on in there. And that's really the bulk of the material we had for today, but we're happy to take on some questions.
Hi, Dave. This is Ben. I just have one thing that I wanted to add, and that is with COVID and with the change in terms of what we're doing in diagnostic imaging, the movement of images from one node to another, one PAC system to another, is actually becoming a very significant issue. And the technology that Ed elucidated also allows us to transmit those images faster, to have a smaller footprint on the PAC system to begin with. And the technology that's been used for a lot of our referring physicians is the compression techniques that are used, and they really degrade the images. So the advantage to some of this technology is that we can increase the speed, decrease the footprint on the actual archiving structures, and maintain image quality.
That's great. Thanks, Dan. Ed, there was a question about sharing our experience, retools for the work, open source versus paid, pros and cons.
Yeah, sorry, I'm just catching up on that here. I also see, maybe before I address that, there was a question about whether or not we used active learning. And I just wanted to point out, in this case, because our objective was around image fidelity, we didn't really have a need to take advantage of active learning, because there wasn't really a need for physician dialogue in the training cycle, which did allow us to train a little more rapidly and a little more autonomously. Experience retools. Yeah, I mean, the most important tool for us in this whole process was really the entire extended TensorFlow suite, which is all open source. And I mean, it's a really high quality suite of tools. And when you look at how far that goes end to end, including tools like TensorFlow serving for building really quick web services endpoints and that sort of thing, it's quite comprehensive. And with the large developer community that's grown up around that, and similar frameworks like PyTorch, I think the open source offerings really cover the vast majority of what a person needs. I mean, there's often cases where you may need a specific proprietary tool, as part of your workflow, but I think in most cases, no, you're going to start with the open source software, and it's going to take care of most of what you need. I'm also seeing another question about limitations of the current CNN model for CT enhancement. There's a few things that I would like to do. I'm just trying to think of exactly how nerdy to get on this, but I'm a big probability nerd, and I think that there's a lot of opportunity here to look at more explicitly developing understanding the probability distributions over the whole human body, being able to essentially build a model that's going to be able to describe sections of images in terms of various learned parameters, and then use those parameters to sort of imagine a whole potential array of bodies. That's kind of similar to maybe some work that folks may have seen around image generation. There's a generation of faces of people that don't exist has been a very interesting topic over the past few years. And there's actually a website called, I believe it's called thispersondoesnotexist.com, and you can go there and you can see a headshot of a human being that's never existed before. And the point of that, of course, would not be just to generate fake CT scans, but if you have the ability to infer from partial information characteristics of a body, that would allow you to create a richer sort of understanding substrate that's going to allow you to generate even more high fidelity images. So that's something that I would definitely like to explore personally. And yeah, I see, Jesse, your CNN tutorial did come through both times there, and that
on my side, so perfect.
And yeah, that TensorFlow tutorial is great. Actually, the TensorFlow website is really well organized and has a lot of very interesting stuff. And like I said before, so as not to take sides in a religious war, the PyTorch stuff is as well. So there's a lot of really, really good material out there and a very vibrant community.
That's great. Thanks, Ed. Yeah, and in terms of what we want to achieve next on the application itself, we're really looking to commercialize this, so to get it out there in practical use and on an active basis through some of the channel partners in the industry. I think most notably like GE Healthcare is one of the biggest providers of CT imaging, and they also have a platform and a developer platform in their ecosystem. So we're looking to essentially integrate this technology into that kind of platform and get it out there globally. So, which I think kind of answered the question that just came up. So the question was, is the business model to partner with an imaging provider? Yes, that is exactly what we're planning to do. So one of the things that GE has asked us to do is to do some active clinical trials on this and gather a little more data behind the outcomes and the results. So we are seeking partnerships to do that, where we can engage both at the data level and at the diagnostic review level, so we can get to that ground truth on images to keep building on the model and building on the capabilities.
And when you talked about basically using this kind of technology to compress basically the size of each of the different packs images, definitely kind of tweaked a nerve in that at AHS we have about 3 petabytes of long-term archive right now and about 500 terabytes of local cache and database space, which it means basically expensive stuff. So any opportunity to kind of highlight the things that need to be highlighted and diminish the stuff that probably isn't as important certainly as merit, for sure, like significant financial merit. So
yeah, and with the ones that we trained the model on initially, the 1,500 images, we're seeing about a 50% reduction in image size, I believe, without a loss of fidelity. So.
There was a question with regard to how would you, if you were to generate images, how would you validate them? And then a second one that just came in, are you working with any data storage providers?
All right, on the validation, I'll throw that one over to Ed.
Yeah, so during training, what we normally do is we can take existing images and then degrade them through a variety of means. Then present those degraded images to the algorithm and compare the output to what we already know as a sort of reference ground truth from the original data set. And that's the most straightforward way to do that. And so we did that both with during training as the algorithm itself is learning, but also to validate the model by taking studies that the model had never seen before, and then again, holding out either parts of that data or degrading that data by other means, running that degraded data through the algorithm without allowing the algorithm to see the original, and seeing how close the result is to the original. So hopefully that answers the question.
There's another question. Is there any danger in manipulating the image to create anomalies?
Yeah, I think there have actually been some there was a recent study that was published out of the EU specifically on that, like how different types of image enhancement models can introduce errors into the resulting image. There are techniques as far as getting down to determining if that's actually happening. So that is really being built into our process, is to do that end image validation to make sure that the techniques that we're using aren't introducing anything that shouldn't be there.
That's great. Can you guys maybe just provide a kind of a high-level overview of the libraries that you use?
Sure, Ed.
Yeah, so the vast majority of what we've done in this model is done just out of the base TensorFlow. Mm-hmm. Some of the original iterations, it involved a library on top of that called Keras, which is now actually built right into TensorFlow.
Precisely.
So yeah. So that makes things very, very easy, and that allows for really rapid experimentation around model architecture, which is great because obviously a successful architecture is not just about tuning hyperparameter numbers, but obviously tuning that sort of broader hyperparameter space, which is the space of all possible model architectures. So it was really, really helpful that way.
That's great. Is there any other questions?
I can ask a couple here. So as part of, so we've started with this 1500 database, our image library. As you are, doing new scans or reviewing scans, are those added? Are those positive results added to that library to build that, or you're just sticking with that base?
No, we're definitely looking to add additional image data as we go here. The more we can build it up, obviously, the finer we can tune that model. And you also need to, generally keep a certain amount of image data in reserve for testing and validation of the model. So, any additional data we can get our hands on, we're excited to do that. So.
And then I had read some interesting work on Parkinson's, where they're actually using CNN to against actually spirals that are drawn by Parkinson patients that can help detect early onset Parkinson's. So
interesting.
Are you looking at expanding outside of a CT, or is that CT is your focus right now?
Right now, CT is our focus, but we, are looking at other imaging. There's a local company here actually that works on ultrasound imaging called Meadow.ai. And they've been having some good success and are growing rapidly right now. So collaborating with them and other companies in this space is definitely of interest to us. So. A question here, I'd be curious to hear how the system identifies features of interest to get the radiologist's additional scrutiny.
So yeah, right now the model as it's built does not flag areas for the radiologist's attention to say, look here. The focus has been on providing images that are as clear as possible and as easy to read, so that those features, stand out and don't just get lost in the noise. I think some of the feedback that we got from Dr. Lindsay's team was that a lot of the low-dose studies were actually really fatiguing to read. You're kind of going through a lot of noisy data and trying to make sure that you're seeing what you think you're seeing and that sort of thing. And then once the image has been enhanced by our algorithm, it's a lot easier to move through that study very fluidly, and anomalies sort of stand out on their own. That's not to say that I think that's an interesting area to extend it to say, even just going back to my previous comment around that probabilistic model, I think if we were able to say, I'm seeing this over here, I'm quite confident that I'm seeing a nodule or something in this space, and that's not normally a good sign. Therefore, I'm going to make sure that that's highlighted. I'm going to make sure that's circled in red for the radiologist. I think that would be a natural extension of that. But yeah, I think that's a good area for future exploration.
Hi, this is Dan. I just wanted to add to this. We've used a fair amount of software which allows us to pick up nodules. So to support the radiologist find the nodule routine, and quite frankly, a lot of that software hasn't really hit mainstream just because it's fatiguing is the word. The stuff that's being picked up is not great. So the ability to actually work with the clinical teams with these algorithms to sort of get a threshold, I think is an area that is going to be very, very important. The more help we can get in terms of not missing something is going to be fantastic. If you can imagine seeing patients that come through continuously with a cancer, and they've got variable size of nodules in their lungs, so we're trying to decide whether the chemotherapy is working or not working. And it's extremely challenging. It has major clinical impacts, and the ability to find additional nodules or to find additional areas within this sea of abnormality would be tremendously beneficial. The corollary of this, and the flip side of this, is that we often see things that are abnormal, and we're not sure if it's a real finding or not. So, for example, if you have a small vessel that's supplying the brain and there's a little bit of a linear artifact or linear structure in it, we will come out and we'll say it's a possible dissection and we need to repeat the scan. Well, there's the potential benefit here of introducing the probability factor that this is likely not real in this environment, which would give us a great degree of, would give us some help or support in not bringing these patients back, because we're always thinking about what's a diagnosis we can't afford to miss, and we repeat and do a lot of additional studies on the results of zero tolerance for error. So in that zero tolerance for error realm, you're going to get a lot of support from the actual clinicians to be supported by AI.
That's great. Thanks, Dan. Ed, did you want to address that question on periodic activation function?
Oh yeah, that's yeah, okay. I I gotta hold myself back a little bit. I find that area really, really interesting. I think you're probably referring to things like the Siren paper around the use of like repeating sinusoidal functions like the sine function as an activation function. I think there's fascinating opportunity there. We haven't looked at applying Siren in particular, just because that's such a new idea. But we did experiment with a number of other activation functions, and we actually found really good results with traditional logistic functions, but also with what is basically the industry standard, and that's the rectified linear unit. I wish I had a more interesting answer for you on that front, but sometimes those kind of standard approaches work well for a reason. But absolutely, that the moment I read that paper, I was flagging that to myself as something I really wanted to experiment with, as we go forward on this.
That's great. Thanks, Ed. And for Dr. Lindsay, there, one of the questions in the chat here is how have the med techs reacted to the radiation changes, image quality, and interpretation arising from the application? I'm assuming Dan.
I had to get off mute there. Yeah, I think that what we're trying to do here is make this system absolutely transparent, so that nobody would even know whether it's being used or not. And even I don't know if this answers the question exactly, but when we did the initial review from the radiologists, we didn't even tell them that they were looking at images that were not that they had no idea which data set they were using. And then subsequently went back and said, which ones do you prefer? And we found that they prefer the ones that had actually been, in quotation marks, enhanced. So the essence here is, if people, let's not change the workflow at all. Let's just introduce something that reduces the radiation and the footprint on the PAC systems, and just work in the background, quite frankly. Like so many things, it's the introduction of technology that doesn't really change what you're doing, but just makes it better. So I don't know if that answers the question exactly, but the essence here is that there really is no impact whatsoever. There's just enhancement. And we're in this game anyway all the time of saying, how much radiation do we use? Do we modulate? I mean, we're using all of these tools on a continuous basis. So this is just one more bullet in our six-shooter, quite frankly.
That's great. Thanks, Dan. Ed, there was one more question there about would we envision using any other modality of imaging in conjunction with low-dose CT for enhancement?
Yeah, I mean, I could definitely see that being promising. At this point, I think as Dave mentioned before, we've been sort of laser focused on CT just to make this model as good as it can be in that domain. So, I mean, that's the kind of thing that we could be looking at as we look at expanding it, but it hasn't been part of our roadmap to date.
Great, thanks, Ed. Are there any more questions? I think that might cover it. So my email is up on the screen, and I think Jesse's, I'm assuming, going to share the recording as well. So happy to talk to any of you on the call today. Feel free to connect with me either on LinkedIn or just shoot me an email, and happy to get engaged in any further discussions. So.
Well, thanks so much, Dave, Ed, and Dr. Lindsay. This is such a great presentation. I really appreciate it, and thank you for your time.
That's great. Well, thank you for having us.
All right, thanks everyone. We'll see you at the next one.
Great.
Thanks.
Thank you.
Take care.